recording and let's see. Oh, I need to get to the right spot. This one. Okay, so if you recall, yesterday we already started CNN, that convolutional neural network, is it? And previously we learned okay, artificial neural network, but CNN is based on ANN, is it? And there is another is RNN, recurrent neural network, okay. But and the DNA is deep neural network, okay. And here basically it's already kind of deep learning, is it? Because if we have a hidden layer. Okay, and if you recall, yesterday we went over the MNIST. The MNIST using CNN, is it using CNN? And I'm not sure if anyone still remember regarding CNN. Generally speaking, you have 3 layers. There are 3 different kind of layers. The first kind of layer, generally speaking, is what? We call it convolution layer. Is it con layer? And after that, you can have, we call it what? Yeah, please. What's the next one? Who remember? It's a pooling layer. Okay, pooling layer. And you can repeat these 2 layers. You can repeat, is it, a number of times. And then you can have flattened layer. Go to the output, is it? And also keep that in mind, convolution layer, generally speaking, the input is 3D. Is it? So far, what we learned is all about 2D data, is it? And the CNN is especially good for image processing because the image itself has image itself is 3D because we also need to consider the different channels, is it? So anyway, so that's just a quick review, okay, for CNN concept. And so if we want to use CNN, is it using TensorFlow? Is it a high-level API? It's Keras, is it? And what over here we do is we use sequential layer. Is it? You can also do functional layer, but we use sequential layer a lot, okay? And for sequential layers, then you just keep adding. It's a layer by layer, okay? And over here, we also need to import the different modules. Is a dense layer, convert. This is for convolution. This is for pooling and for flatten. And today we will also explain the meaning of dropout layers. So they are all layers. So it's already being defined by TensorFlow so that we don't need to rewrite everything from scratch. Is it? Because if you use a low level, just remember the TensorFlow has a low level API, is it? Then in that case, you need to build the TensorFlow graph, is it? So that's quite comprehensive, is it? Complicated. And simplified of the work is a high level API, is it? And we have TensorFlow's Keras. So it's from Keras and it's much simpler. So you just specify you're going to do the sequential model, then you just add different layers, okay? So this is, so the other part, if you recall, yes, it's pretty similar, is that it's the training data testing data from MNIST. But here, because of the 3D requirement, is it? So we reshape our training data and the testing data, okay, so that it only has a single channel, okay, because the original we just have the 2D image, so we manually add a channel, okay, add a channel. So this is reshape, don't forget about that. And also remember, with neural network, is it, generally speaking, we need to normalize data, is it? So this is regarding data pre-processing. So you need scaling, is it, and to bring all the data into the same scale, is it? So here we do normalization so that data can be distributed into between 0 and 1, okay, scale. So don't forget that. And then if you recall here, is that we said, okay, our model is going to be sequential. Is it? After that, then we add a convolution layer first. So this convolution, the first parameter is the number of filters. Okay, so the number of filters then will determine the depth of the output. Okay, so then the depth of the third dimension is going to be 32. Okay, it's going to be, and this 3 by 3 is the filter. Okay, filter. So basically, it's 3 by 3 by 1. Okay, it's 3-dimensional. We add the channel. We only have a single channel, is it? And the input image is 26 by 26 by 1, is it? So that's pixels, okay. So it's a 3D. So we first go over convolution, is it? And we use rectify linear unit to do the activation, okay, do the activation. And then we do the pooling, is it? The purpose of pooling is, who still remember the purpose of pooling? Pooling layers purpose. Who remembers that? Is to decrease the size, is it? Decrease the size, is it? Especially for image, you can, like in this case, it's 2 by 2. Then that will make your image, is it? After the convolution, after the pooling, it will decrease by 2. Okay, so if it initially it's 26, then it's go to 13 by 13. Is it? And because you have 32 filters, so that's why the third dimension now changes to 32, from 1 to 32. Okay, to 32. And then next we have flatten layer. Okay, flatten layer. And after flatten, then we are going to go through the general neural network as the activation with rectify, and then the last output we deal with the softmax. Okay, and in TensorFlow there is a very nice method to report your model. So if you take a look over here, and if you want to know, oh, what my model look like, is it? It's data, it's information. Then you just call the summary. And what the summary is looks like below, is it? It tells you layer by layer, is it? Here is first of all, it's convolution 2D layer, is it? And what the output shape, and the total of parameters, is it, for this layer? And then next it's maximum pooling layer, is it? Maximum pooling layer, and it's shape. Is it? And after that, we go through flatten, is it, to make it to one-dimensional in this case, is it? So that's the output shape. And then we go through another layer, another 3 layer, is it? So for this one, it's so you change it from 5408 to what? So here you only have 100 neurons, is it? And another 100 neurons. And the last layer is you only have 10 neurons. Is it? Okay, so it gives you all of the output, is it? So you can use this to get more detailed reporting, is it? And it also shows you the total parameter, trainable parameter. You can see it's quite large, is it? That's why we see we need a deep learning, as a TensorFlow then in this case. It's more efficient than the classic neural network approach, okay, because you can clearly see there are so many parameters, is it? And another nice thing for TensorFlow is you can also have an image of the model, okay? And if you want to do that, you can just call plot model. Okay, and you import the plot model, and it's in Keras utilities. Okay, and then we can also visually see the model layer by layer. Okay, and I can show you what it looks like. Let me find the, yeah, it's here. And you can get the image output of the models. Is it like clearly over here? Is it? It shows you, okay, the convolution layer. The convolution layer, the first, is it what is input and what is output? Is it? It's changing from 28 to 26 by 26 and 32. Is it? Because we apply 32 filters. Is it? And each filter can catch different features. Is it? So that's how, because initially the third dimension is 1. Is it? And then next you get to pooling layer. Is it? Pooling layer input is from the previous layer, and the output you can clearly see. Is it? It's decreased by. So it's shrinked by 2. Is it? By 2, is it? So that's why we see pooling layers purpose is to decrease the size, is it? And then next you do flatten, is it? Because here is 3D and here is just 1D, is it? So you flatten layer and then you can do dense layer, is it? So you decrease, did you see the input from 5,000 to 100, is it? 100, so because over here you have 100 neurons. And then over here, you decrease another, is it, from 100 neurons to 10 neurons, because we only have 10 images to classify, is it? That's why the last layer's output needed to be 10, is it? And here we also see another layer, we call it a dropout layer, okay? So the dropout layer, the purpose is, because the image, over here, we can also apply the convolution neural network for images, because the image itself also has the sparsity. Is it? Sparsity. And also not too close related to each other. Like suppose this is a corner and this corner, is it? And these two not rely on each other a lot. That's why we can apply convolution and drop out because you can see, is it? If you recall, we have over millions of parameters. Is it to train? Is it? So it's a lot of work, and it may lead to overfitting. Okay, with deep learning. Okay, so how we solve the problem with the dropout layer? Dropout layer, the goal is you purposely pick certain output and make it to 0. Okay, so that it won't have any effect. That's why we call it a dropout. So you drop out some weights, kind of, is it? And then, in this case, we can avoid the overfitting issue. Okay, so that's a purpose for dropout. And then next, let's see. So over here, yeah, over here we did add the dropout. Is it? Oh, sorry, I didn't share, I think. I need to share. So over here, we have the dropout layer. Is it? Add a dropout layer. The dropout layer, the percentage of the dropout here is 50%. So you set 50% of the output from this layer to the next layer, you drop them off, you make them to 0. Okay. So that's a purpose of the dropout layer, okay, to avoid overfitting. So after that, then, oh, we already discussed the plotting. So after you create the model, and then next is you compile the model. Okay, compile model, you need to define the optimizer. The optimizer is the gradient, related with gradient. Is it? And over here, you choose adder. You can also choose stochastic SGD as a gradient descent. Okay, and then the loss. Is it the way to calculate the cost or the loss? Here we use sparse categorical cross entropy. This sparse categorical is for multi-classification. Okay, and also the performance matrix. Here we say, okay, we are going to use the accuracy, and then you can fit the model. Okay, when you do the fit the model, you specify how many number of epochs you wanted to train, is it? And the batch size, is it? And do you want to see the each epoch's output? Here it says 0, that means it just keep run until the end. Finish running, then it will give you the report. Otherwise, you won't see any intermediate steps. And after that, you can evaluate the result. Is it with testing data? Okay, and you can also do the prediction. Is it? So that's about this CNN example. Okay, so we finish that, and the next, let's see, we can move on to the next one. It's to discuss, show you the example about the effect of dropout. Okay, so here the dropout we already see is that it's just randomly setting the outgoing edges, the weight to 0, so that neuron make up the hidden layers, okay, to 0. So over here we use MNIST again. Okay, so we are going to do, this is not a CNN, okay, this is just a regular ANN, but we try to see how the dropout works. Okay, so nothing new here regarding the data pre-processing, is it? And with regular neural network, is it? And over here we use sequential. Okay, then the first, in this case, definitely you need to flatten, is it? Because the input is 2D. And then the first one, the input layer is 128. So this is input layer. is it you have 128 neurons, is it because you specify the size. And the activation, is it is you apply what? Rectify linear unit, is it? And after that, you said, oh, I'm going to add the other layer. It's dense, it's 100. This is the second layer, is it? So this is a hidden layer, basically. In this case, is it 128, is it? And it's still the active. So for each layer, you also need to specify the activation, how you are going to activate, is it, to find the output, is it? Okay, so then the last layer is as the dense, in this case, is it? So this is output layer, is it? And you have 10 neurons, is it? And the activation is softmax in this case, is it? Use probability, is it? So the output should be between 0 and 1 as a probability, okay? So then you have this connected, is it? So this is, so over here you see this is sequential model. So you just add layer by layer, okay? So this is, and we can have the layer output, the model output, okay? So anyway, so this is just a very regular 3-layer ANN, okay? So pretty simple one. And here it shows you the information about each layer, is it? You can also generate the plot of the layer, as I see the relationship more clear, is it? Over here, you can also see the trainable parameter is quite large, is it? And then you compile. When you call compile, you need to specify the loss function, optimizer, and the matrix, the performance matrix. And then you do fit. As a fit, you need to specify the epochs, batch size. And over here, I also specify, because I do cross validation. If you recall, previously we discussed k-fold as a cross validation. So here we also specify, okay, I'm going to use 10% of the training data for validation. Is it? Okay, so that's regarding the fit part. And if you take a look over here, I said the verbose is 1. Is it? When verbose is 1, you will see the training step. Is it? Okay, the first epoch, is it? So this is a progress bar, is it? And how much, how long it takes, is it, for each sample? What is the loss? What is the accuracy? The accuracy. So it reports you the loss, the accuracy, and the validation loss, and the validation accuracy. Is it each of it? Is it each epoch? It will tell you the result. Is it? And if we keep looking, so each epoch it will let you know the result. Is it? And basically, with TensorFlow, you can also draw plotting the training and the validation accuracy for the epoch. You can plot the relationship graph so that we will visually can see if this model is good, efficient or not. What you can collect is it's called history. And then you specify, okay, I want to collect the loss and the validation loss. Is it? Then I'm going to plot the loss against the epochs. Is it? Against the epochs. Okay, then let's see. So this is the output, is it? So this yellow line is a training loss. And this red line is a validation loss, is it? And you can kind of see at the third, after the third epoch, is it? The validation loss, it's kind of flat, is it? So even if you add more epochs, it's kind of just flat, not a lot of change, is it? And also you can see these two cross with each other, is it? And previously, if you recall, we learned the learning curve kind of concept, is it? And the validation curve, is it? So this is not, you can then kind of clearly see this is not a good model, is it? And over here, you can also collect accuracy and validation accuracy. And we can also plot the accuracy versus the epochs. Is it? It's similar. Is it? Similar pattern. Is it? It's cross. And also kind of at the third epoch, the validation didn't improve. The validation result didn't improve. So this is not a very impressive result, okay? And then next, let's see. Over here, we use a new model, okay, this time, sequential. And after this dance, is it? This is the input layer. I add a dropout layer here. So after the input, you add the dropout. But make sure, okay, dropout is before the ReLU, okay? So dropout, generally speaking, can be anywhere. But the exception is don't put it after activation. Generally, it should be before ReLU, okay? So this is just an exception, okay, ReLU. So I add a drop off, 50%, is it? And over here, same thing, I add another drop off. So here I add two dropout layer, is it? And then let's see, so this is a model result, is it? So over here we have dropout and we have the dropout, is it? And then next, the same thing, we compile and we fit, is it? And we have the accuracy. And this time we plot the loss versus the epoch, is it? And this time you can clearly see the training and validation didn't cross, is it? And you can also see the validation. It's not after the third, it's go to plateau, is it? It's kind of keep changing, is it? And there is also some offset, is it? Offset. So this indicates after we consider dropout layer, after we add dropout layer, is it? It's better, is it? The training result is better, is it? It's better. So, and especially here, we didn't cross, is it? So that means the overfitting issue at a certain level, is it? We avoid the overfitting issue, okay? And same thing, you can also plot the relationship between accuracy and the epoch. Is it like this one shows? Is it? So it's clearly see is it looks better, it looks better, especially in this case. Did you see the validation accuracy? This is the ideal. If you recall previously when we learned learning curve, it's the ideal. The validation accuracy is higher than the training. So that means you don't have the big issue of overfitting, is it? Okay. Okay, so that's regarding this example. Okay, then let's see. So this example, okay, and the next one is pretty straightforward. It just shows you from another angle. Okay, so this is also about CNN, convolutional neural network. Okay, so to classify some image. Okay, this is from TensorFlow website. Okay, by image classification. And so it's pretty similar as the MNIST. Okay, so you get the data, you load the data, you normalize, is it? And here it shows different images, is it? And what next? And here we said for CNN, is it? We prefer to use the rectify linear unit, is it? And this is also true for ANN, okay, in deep learning, is it? We didn't use sigmoid. No, not sigmoid, so instead of sigmoid or tangent. Is it or tangent? The reason is because these two can lead to the issue, we call it gradient disappearing. Issue, okay, or not disappearing, vanishing gradient issue, okay, with rectify, because rectify it looks like, is it linear? Is it? It's max, 0, and x. Whatever import, is it? It only takes the positive. Otherwise, it will just take 0. Is it? Versus sigmoid, it's something looks like this. Is it? So sigmoid and tangent can lead to vanishing gradient problem. Okay, so that's why in neural network, we see ReLU a lot. Okay, so anyway, here we have convolution and pooling, another convolution and pooling, is it? And generally speaking, these two pair together. Okay. Okay, you don't just from nowhere you come a pooling without a convolution. Okay, generally we don't do that. Okay, and after that we have another convolution, is it? And we select the activation. Activation is rectify linear unit. Okay, so this is our convolutional neural network model. Is it? Here is what the model looks like. Is it the output shape? It also gives you. And then what next you can do is, okay, we haven't finished. We add a flattened layer, is it? So this part is the regular neural network part, is it? You have the activation, and then you have the, so generally speaking, softmax is used to last layer. Okay, it's the output layer. Generally, okay, so keep this in mind. It's for output layer. And then you compile, same thing, we use add, sparse category, cross entropy, and accuracy, is it? And then you fit the data, is it? You do fit, you do the training, is it? And over here, same thing. We can collect the history, is it? And what history include? History is the dictionary, is it? Has loss, accuracy, validation loss, and validation accuracy. Previously, we already see, is it? And here again, we can also plot the kind of like, but this is not exactly like a learning curve, but kind of like the learning curve, is it? So it's accuracy versus epoch, is it? And this is validation, and this is the training accuracy, is it? And we can see this is not a good model, okay, not too good, this one. And the accuracy is also pretty low, is it? Because the ideal one should be what? Should be your validation is on top of the training, okay. Okay, so that's regarding, and the same thing for the loss, is it? You can also plot the loss through the history with the collection of the loss data, is it, versus the epoch, okay. So here you can also clearly see, is it because both cross to each other, it's not a good model, is it? They should have some offset. And regarding the accuracy, so for accuracy, it should look like something like this. So this is validation, this is accuracy, then this is good, okay. For loss, it's the other way, is it? Other way. So this is for training, is it? And this is for validation, okay, because validation's loss is even smaller, is it? And they have offset, is it? They not cross, okay. Then this generally, in these two cases, we say it's good, is it? Your model is good, okay. Okay, so that's the regarding CNN, okay. And what next we are going to discuss today is we will start the last topic, okay. It's about reinforcement learning. Reinforcement learning, okay, especially Q learning and deep Q, okay. It's quite interesting, okay, the topic. And also it's very comprehensive, okay. We will just get some basic idea. Okay, so here is an overall review about machine learning. Is that we learned supervised learning, is it, for classification, is it, and for regression, is it? So this is classification. Is it for discrete data? For continued data, we said it's regression. Regression, is it? And we also learn unsupervised learning. Is it clustering? Is it hierarchical clustering, if you recall? Is it clustering? Okay, so the third category in machine learning is called reinforcement learning. So we haven't learned this category yet, is it? So what reinforcement learning is, you have some agent, okay. The agent learns to interact with some environment to achieve some reward, okay. So this is different from supervised or unsupervised learning, okay, the concept. And reinforcement learning, is it, if you recall, there's something called deep mind, is it? It's deep mind is like combines deep learning technique with reinforcement learning, is it, handle some complex learning problems like AlphaGo, okay. So you may hear that a lot, okay. So anyway, that's deep mind, is it? And the deep Q, is it? So because here it combines deep learning, is it? So TensorFlow and the reinforcement learning together. So we call that deep Q. And the reinforcement learning, the basic one we will learn is called Q learning. Okay, so it's based on some Q values. And we will use an example about the kind of like automation, taxi driver pickup and drop a passenger, etc. Okay, reinforcement learning, the key concept in reinforcement learning is you have some agent. Okay, agent going to observe some environment. So here you have the concept called current state. So it's based on state change. Okay, but the agent needed to act with some policy, or we call strategy. Okay, strategy, and take some action. And when the agent take the action, then the state is going to be, you're going to transformed from the current state to the next state. Okay, and when you take some action and you transition from one state to another state, you will receive either reward or penalty. Okay, this is also like you play game. That's why reinforcement used a lot in games. Okay, game design. Okay, and you want to find the best strategy. Is it like you play chess? Is it best strategy? Is it you want to reinforce the policy, that's the best strategy, the optimal strategy, is it? So that's called reinforcement learning. And you want to maximize the long-term rewards, is it? Okay, so this is some key concept in reinforcement learning. Okay, so here we also show the reinforcement learning, the kind of process, is it? So we have some agent, is it? Agent observe the environment, is it? And the agent can take some action, is it? At a certain stage of the learning, is it? Of the learning. And then it can get reward or penalty at the current state, is it? And you're going to feed the current state and the reward plus the next. So this is the next state. So if you take a certain strategy, you will go to the next state, and you may have some reward and the penalty, is it? So you're going to also get this to a table, we call it a Q table, and the current one also fit into that table. And the Q table then updates. So you kind of keep doing like this. And the goal is to maximize rewards in this game. Okay, so that's the general idea. Okay, and in reinforcement learning, it lies between supervised learning and unsupervised learning. Okay, and you said we try to maximize rewards. As if we try to maximize, but be careful, being too greedy doesn't always work because it may lead to overfitting. Is it overfitting? Okay, so that's not good. So we try to optimize for the maximization of your reward over the whole training. Okay, over the whole training. So in that case, it says the reward the agent receive not just depend on the current state, but the entire history of the state. Is it entire history of the state? Okay, I'm not sure if you learned like, so this also has some kind of concept, but not exactly like that, but they have some similarity. If you recall in graph, you learn digest search, is it? Routing, is it? The link state routing, is it? In that kind of they also have some similar, but that's take the whole topology, is it? The whole graph, is it? Here seems it's the history, is it? The whole history. Okay, so over here, what we are going to see is example is about a self-driving taxi. Okay, self-taxi. So it's a, we call it a smart cab. Okay, so it's going to pick up some passenger. at some location, okay, and then drop off at the another, okay, and you have some basic task for the smart cap to take care of. Is it you want it to drop off the passenger to the right location? Okay, if this is the case, then you give some rewards. Is it driven? And of course, you want to save passenger time by taking minimum time. Is it? You don't want to take a detour. Is it? So kind of like the find the shortest path. Is it? Okay, you also forgot, so you need to take care of the safety and the traffic rules. Is it? Traffic rule. So how do we achieve this goal? Is it? So we can use reinforcement learning to solve this problem. So here it has some key concept from reinforcement learning. It has state and action and rewards. Okay, so that's go to, we call it Q table. Okay, and of course Q table calculates Q value. Okay, but the Q value depends on rewards. Okay, rewards. But the rewards is not just the current, it's also the rewards that comes from two parts. The current state rewards, this is immediate feedback rewards, is it? So it's kind of greedy, is it? And the next state reward, is it? And when you pick the next state, so then over here there are two ways. One is called exploitation. You exploit, you take advantage of something, is it? That can lead to greedy. Okay, and the other approach is we call exploration. Okay, so if the exploration is just some random way, okay, random pick the next state. Okay, so when you pick the next state, you want to find a balance between exploitation and exploration. Okay, you don't want to be too greedy, but of course you want to maximize the rewards. Okay, so you want to, so that's why we always say you want to optimize. Okay, optimization, is it? So that's the goal here. Okay. Okay, and I think we kind of run out of time today, so we